Hello. In the last video, we discussed what a limit is and a couple of ways to think about the limit graphically, maybe how to begin computing a limit. In this short video, I just want to talk about the different ways that a limit might not exist. When a limit DNE stands for does not exist. Okay, so one of these ways we already talked about, the infinite discontinuity or the vertical asymptote, often found with rational functions or any time that you end up dividing by 0 in your function. So look at the limit as x approaches 0 of 1 divided by x squared. This limit does not exist. If x gets close to 0, 1 over x squared doesn't get close to any number. It just gets bigger and bigger without bound. Now, if you want to give more information, it's okay to say that this limit equals infinity, but realize infinity is not a number, so this limit doesn't really exist. Saying equals infinity is just a way of explaining why it doesn't exist, giving a little more context. A second kind of reason a limit might not exist is a jump discontinuity. Okay, so let's remember this function that you might not have used very much in pre-calculus, but it's the step function, okay, or the greatest integer function. So this function is basically the rounded down function, right? If you get an integer for x, then it just spits back to the integer. F of 0 is 0, f of 1 is 1, f of 2 is 2. But if you get something between an integer, it'll round it down to the nearest integer. So f of 1.5 is 1, f of 2.2 is 2. Okay, so the graph ends up looking like disconnected line segments of length 1. So, what's the limit as x approaches 1 of this function? Well, if x is close to 1, then f of x is also looks close to 1, right? F of 1.1 is 1, f of 1.01 is 1. But wait a minute, if x is close to but less than 1, then f of x is going to be 0. F of 0.9 equals 0. F of 0.99 is 0. So this limit doesn't exist because the behavior of the function is different depending on if you're slightly greater or slightly less than 1. Here, it doesn't really matter that f of 1 equals 1. Right? Remember in the first lecture we said the limit cares about what happens when x is near but not equal to its limiting value, so we don't care at all that f of 1 is even defined. So if you want to give more information about this, then we can say that the limit of the step function when x approaches 1 from the right, from positive numbers, from numbers bigger than 1, that limit equals 1. The limit as x approaches 1 from the negative side, from numbers slightly less than 1, of the step function is 0. Okay, so this way of splitting the left and the right side up will become a little bit more important later, but I wanted to give you a preview of it here. So the jump discontinuity. Graphically, a limit doesn't exist if the graph has a jump or a step. The third way, let me give you one more example because it'll be a really useful example to know. They actually really love this example on the AP test. I don't like the step function too much. Absolute value x divided by x. So if you think about this function, if x is a positive number, then the absolute value of x is just x. So x divided by x is 1. So it's 1 if x is bigger than 0. If x is a negative number, then absolute value of x is minus x. So it's minus x divided by x. So it's negative 1 if x is less than 0. And g of 0 does not exist. All right, I would be dividing by 0 here. So the graph of this function, it's negative 1 for negative x. Don't include the endpoint because g of 0 is not defined, and then it's positive 1 for positive x. And again, don't include g of 0, don't include the endpoint of this line. So this is another really famous example of a jump discontinuity that you should be familiar with. This one, and maybe you can replace x by some expression, right? Absolute value of sine x divided by sine x, for example. The graph would look different, but it might still have a jump discontinuity. Okay, the third kind of reason why a limit might not exist would be that it just oscillates too quickly or chaotically as you approach the limiting value. So here's a nice, nasty little function, sine of pi divided by x. All right, so I'm interested in the limit as x approaches 0, and I don't know much about this function, so I'll try the table of values method. If I plug in 1/2, then that's going to give me f of x is 0. If I plug in 1/10, I'll also get 0. Plug in 1/100, I'll also get 0. Double check this on the calculator if you want. But you look at this and you might think the limit should be 0. Inputs getting closer to 0, outputs staying right at 0. But in fact, this limit does not exist. If you look at a graph instead of just a table, you'll see a really hard to interpret graph. It starts off smooth when you're far away from x equals 0, but as you get close to x equals 0, the function oscillates more and more rapidly. It's completely chaotic. When x is close to 0, you might be any value between 1 and -1. So there is no limit. It's a chaotic oscillation. I'll give you one more example for this, which I think is in the homework, but just for fun. You don't have to even use a pre-calc function to create chaos. You could use a piecewise defined function. So let's make g of x be 0 if x is in Q and 1 otherwise. So do you guys remember this symbol, bold Q? You might not even have seen it. This means rational numbers. So if x is a rational number, then g of x should be 0, and g of x should be 1 if x is an irrational number. What is that graph going to look like? Well, we can plot some points to start. Let's see, let's put 1 here on my axis. So when g of 0 is 0, g of 1 is 0, g of a half is 0, g of a quarter is 0, g of an eighth, g of 3/8 is 0, g of 1/16, 3/16, 5/16, 7/16, 3/4. You know what, if I keep going like this, my pen is too thick. I'll eventually put a dot everywhere on this x-axis. I mean, my dots will completely cover it up. But the problem is that in between every two rational numbers, there's an irrational number. So somewhere in here, I'm going to have a dot. I'm going to have an irrational value of 1. Somewhere really close to, but not right at 0, I'll have another irrational number. And I'll have another kind of in between every two rational. So if the rational numbers are so packed closely together, closer than the thickness of my pen, then so will be the irrational numbers, and the graph won't even look like the graph of a function. I'll have all these points clustered together up here, all these points clustered together down here. This function is limit as x approaches c of g of x does not exist for all values c. So this function is a good example of a function which is discontinuous, not just at one point, but everywhere. All of these functions, this is chaotic right at 0, but if I wanted to find the limit as x approaches 0.1, it's actually a continuous function at that point. I could just plug it in. This guy has all these jump discontinuities, but on the line segment, it's continuous. It's the limit exists everywhere except for the jumps. So this is a good kind of mind-bending example. Think about it a little more, I think, and maybe you can get the point. The last reason why a limit might not exist is a little bit of a silly reason, kind of a special case. If you're asking for a limit point, which is just outside of the domain of the function, then the limit doesn't exist. So I don't like calling it out of domain, because if you have a whole discontinuity that we saw in the last slide, in the last lecture, you could have a a value which is not in the domain of the function, the limit might still exist if it's a hole in an otherwise continuous graph. So here, it's not really a case that will come up often, but if you're asked about a limit of a point which is kind of not just a single isolated point outside of the domain, but way outside of the domain, then the limit wouldn't exist. So what's the limit of square root x as x approaches -2? I mean, it doesn't make any sense. Square root has domain positive numbers, -2 is way out here. If x is close to -2, square root x has no value at all. So the limit just doesn't exist. So that's a kind of domain restriction. But again, that one won't come up as often as the other three.